Okay. So now we are going to talk about DHCP. DHCP stands for Dynamic Host Control Protocol. Basically, the issue was that before this protocol, everybody had to assign the addresses manually to every computer. And that was too much work. So they said, why don't we just write a program that will assign the addresses and keep track of who is using, which computer is using what address. And so basically it allows the host to get an IP address automatically. Nowadays, all the routers have DHCP. And in some cases, we don't want to use the DHCP in a router, then we use our own DHCP in another computer, and you can do that. Basically, what happens is the DHCP server's address has to be programmed in the computer, and generally that is the default router. So whenever a computer comes up, it goes to the default router and says, tell me what is my address. So what the router does is gives the address on a lease. Lease means it is good for 24 hours, or it is good for 4 hours, or it is good for 4 days, or for a month, or whatever time you want to put that. Generally, by default, it is 24 hours. And after 24 hours, that address is taken back unless you go back and renew the lease. And if you renew it, you get the same. Generally, you want to get the same address because you don't want people to get confused. But it might have gone to somebody else. If you didn't renew it, then it might have gone to somebody else, and then you will get a new address. And so to get that DHCP address, the host sends a broadcast request, which goes to 255.255.255.255, which means to everybody in the world, basically. I mean, it doesn't go out of the network. So this is one of those addresses that stays in the local area, and therefore it says, is there a DHCP server here? And if there is a server, it says, yes, I am here, and my address is such and such. And then you can say, okay, my MAC address is this. So question is, what is your MAC address? And this is important because in this course we are going top down, and one of the problems with top down is that the network was designed bottom up. And so I have to explain to you the MAC address first. MAC address is your Ethernet address, and the Ethernet address comes in 48 bits, and 48 bits are generally written in hex. So they are written as like 01:, AB:, C0:, something like that. We'll have 6 bytes. Each letter there is actually, each letter in that MAC is a hex bit is 4 bits, and therefore you get 48 bits. So you send your MAC address, and the MAC address, interesting thing about the MAC address is globally unique, so that nobody else can have that MAC address. So it knows exactly who you are, and you can program in your router that if this MAC address comes in, give it this address. And I have programmed that, for example, in my home. Whenever I connect my main computer, it always gets a particular address because I want everybody, all other computers, to know what that address is, and I don't want to program it every day. And so similarly, there are other computers in my home, and there are other cameras in my home. As I said, they all have a very previously assigned address based upon their MAC address. So anyway, so based upon the MAC address, you get that. So here is the total thing shown in this picture. Arriving client is on the right. It sends to the server that I don't have my address. Its source address is 0000. So the IP address at the source is 0000. Port number 68. The destination is 255.255.67, and then basically it says that it sends the message. It sends the message to the world, and the DHCP server says, okay, my source address is 223.1.25, and the destination is basically sent to you. And the reason it comes to, even though the IP address is 255, it will have the MAC address, and when the packet is sent, it also has the MAC address at the layer 2. And so the layer 2 means you will pick it up, and it will say that the address that has been assigned to you is 223.1.2.4, and then lifetime is 3600 seconds. So 3600 seconds is 1 hour, right? So in this case, you have this address for 1 hour. So now it says 32.1.25 DHCP discovery message, this is DHCP offer message, this is DHCP request. So this is the request, and this is the ACK. In the ACK, you get the address. Yes, I was basically 2 steps ahead here. In the request, basically it is a broadcast which says that is there anybody here, and they say yes, I am here, and this is my address. And in this case, it says that I would like to get this address 223.1.24, and this says that yeah, you got that address. Now the thing is, this is the address that it wants, and that may be because it had that address before and it wants to keep it, but it may not be the same address that is returned to you. Okay, so that is the DHCP. It's very simple protocol basically. What this picture doesn't show, and this picture is a little bit old because it doesn't show the MAC address. One of the key fields in these things is the MAC address, and the MAC address, actually the Ethernet came in 1980, and this might have been before 1980 or whatever. So basically the MAC address is the one that really is responsible for DHCP address assignment. So there is a lab, and this is a very simple lab actually. In this case, you just have to download a trace from the author's website, and then once you download it, you can load it into Wireshark, and in the Wireshark then you can see all the packets going back and forth, and then you can examine the frames 4, 5, 6 as it says, and then answer all these questions. Okay, all of these answers are in the packets, and so this will help you once you do this lab. This will help you understand all these things. One of the ways to do this lab would have been that rather than downloading the trace from author's place, you could have monitored it on your Wireshark. You have Wireshark, and you could do a DHCP request. But I think that there could be some problem with that. But anyways, I mean, you probably might need 2 computers or something. But anyway, here, and this is all given to you, and all you have to do is just look at the trace and find out what are the fields and what are the things they are saying. Okay, that finishes IPv4 actually. Unless there are any questions about anything, we have just covered DHCP so far and NAT. But now IPv6 is another solution which came up in 1991. And by 1991, the issue was that all the addresses were kind of exhausted, IPv4 addresses, and so they had a competition, and many people submitted solutions proposals. And one of the proposals, which came actually from a Stanford student, was that why don't we change the addresses to 256 bits. 256 bit was considered too large, so basically, and 64 bit was considered too small. So 128 bit is what they agreed upon finally. So the addresses became 128 bit in IPv6. With 128 bit, you can have 10 raised to 38 addresses, which is a lot of addresses. And if you had computers like 10 raised to 21 computers on every square meter of the Earth's surface, each of them could get the addresses. Okay, And so this is a very large number. And they said that even if we assign a million address per microsecond, it will take 20 years. So this is a very large number. And in fact, it is larger than what we need, but it is there anyway. Now, the problem with 128-bit is that you could not really write it in decimal format like we used to write before. So the previous format for IPv4 was dot decimal. Dot decimal means that we have decimal numbers separated by dot. And dot is a decimal point, and therefore it indicates that these are decimal numbers. And for IPv6, basically it was decided that we will have colon hex notation. Colon is used to separate the bytes, and hex is where they are written at, actually. So they are written in 2 bytes at a time. So FEDC is 4 bits each. Each is a hex number, and 4 bits each is 16-bit. So you have 16-bit colon 16-bit colon 16-bit colon 16-bit, like 8 times. Okay, and that is how you write the IPv6 address. Now this could be very long, and so there is a way to shorten it. Anytime there is a 0 in the front, 0 in the front of any word, you don't write it. For example, if it was 0 EDC, you don't write 0, you just write EDC, and people will know that there is a 0 in the front. Second thing is, if you have lots of zeros in a sequence, then you can write 1 time only, not 2 times. Just once you can change a sequence of zeros to 2 colons. So right here it is written as FEDC colon colon. Okay, that means there are some zeros here. We don't know how many zeros are missing, but some zeros are missing. And then you count the rest of them. So the rest of them is 1, 2, 3, 4, 5. So there are 3 zeros missing in the middle. Okay, 3 0 0 0 0 0 0 0 0 0. 3 16-bit zeros are missing. Okay, now you cannot do that same thing to skip the next set of zeros, because if you did that, then we wouldn't know how many zeros are where, right? So it's very straightforward. Only zeros once you can skip with double colon. And here is another example. We put a double colon, 3 2 4 3, and so on and so forth. So how many zeros are missing in the front? Anybody? 4. Good. So raise your hand too, so I know who did it, and you get a credit for that. So anyway, yeah, I got it. Okay, so basically 4 zeros are missing because there are 8 of them total has to be. So we'll write 4 zeros in the front. That would be 64-bit. 16 times 4 is 64 bits are missing. Okay, we can leave the last 32-bit in dot decimal, because most of the computers will really have zeros in the front, are fixed quantities in the front. The last would be your 4 bytes would be, your 32-bit, last 32-bit would be mostly your IPv4 address. So those can be written in dot decimal. So for example, you can write down like this, colon colon 128.23.45.88. So this is point, means these are decimal numbers, and they add up to 32 bits. Everything else is a 0. Okay, everything else doesn't have to be 0. You could also write something else there, but if you want to have something else, you have to just write that something else in hex. Okay, now can you specify a prefix by length? So just like we did it with the IPv4, here we are specifying the whole thing and then saying /50 means take the first 50 bit of here. Now, how many bits are specified? Can anybody count how many bits are specified right now in this? 48. So 2 bits are not specified. Basically, what it is saying is that rest of them are zeros by having this colon colon. So you will take these 48 bits plus 2 zeros, and that is the prefix. Okay, and whenever you match the prefix, you will match those 2 zeros as well. All right, so the prefixes are specified like this. All right, so what we have done so far is just talked about how the addresses were done, IPv6 addresses, and how they are written. But the IPv6 packets are also very different. IPv6 packets are different because IPv6 decided to change the head totally the whole format. It's not just the thing address alone. So here is the IPv4 packet shown from before in the bottom, and IPv6 is shown on the top. So the first 4 bits are version number. Everything else is different. Then we have 8 bits of traffic class, 20 bits of flow label, 16 bit of payload length, 8 bits of next header, hop limit, source address 128 bit, and destination address 128 bit, and that's the end. So what they decided was, because the addresses are so long, the header would be very, very long if we put any more fields. So there's all other fields are optional, and these fields are required, and so this is called the main header. And then there could be other fields. They would be in some other header, next header, and that is given here, next header. Next header is basically the next, and we will show you the next header. There are many different kinds of next header. So those will be coded in the 8 bits here. Hop limit is same thing as the time to live. We had time to live before, which was actually never was a time, it was always a hop. So here they changed the name to hop limit. And flow label. Flow label is by the time IPv6 came, by the time of 1994, they started thinking about that we need to separate when we want to give any quality of service, we need to separate all the packets belonging to a particular flow. For example, right now we have a video flow going to you, or an audio flow going to you. Each of these needs a different treatment, a different quality of service. So that would be a different flow label. So each flow is specified by a label, and then the class is specified by the 8 bits. The 8 bits will indicate what kind of traffic it is, so that the network can treat it accordingly. Now, this is only the main header. There are many, many extension headers, which unfortunately we don't have time to talk about. They might be in the book, but basically what happens is, such as fragmentation header is one of them. So we talked about fragmentation on IPv4. There is fragmentation in IPv6. Actually, it is kind of not encouraged, but whatever else you need to do, there is a header for it, and that will have a header type, and it will have similarly a next header after that. So you could have 4, 5, 6 IPv6 headers, one after another. Okay, the last header will say in the next header field, this is a TCP packet. So then it will show you the next layer, layer 4. So before that, you might have many, many headers of IPv6 alone of itself. All right, so the IPv6 versus IPv4 is 95 versus 75. Basically 20 years of difference. In 20 years, a lot of things we came to know. IPv6 is only twice the size of IPv4. So the header is twice the size. This is actually a lie, because we are just counting the main header. Main header is twice the size, but the actual number of headers is much larger, and therefore the total number of header size will be very large. Only version number is the same position. They remove the header length, type of service, identification, fragmentation, checksum, and header checksum, no fragmentation. So there is no fragmentation basically because it says header checksum, which is not even in this field. Hop limit, destination address. So I don't know where the header checksum field is missing. But anyway, datagram length replaced by payload length. So this is a payload length, which clearly means that this is not the length of the whole datagram from beginning to the end. This is just the thing that came from layer 4. And then protocol type replaced by next header, which we said the next header is what is after this header. Time to live replaced by hop limit. Priority and flow label were added. So this time traffic class has a priority inside it, and the flow label was added. All fixed size fields. There are no variable size. Like the options previously were variable size. No optional field replaced by extension headers. Those are the other headers. That an 8-bit hop limit, and the hop limit is still 8-bit. You see 8 bits here, and it was also previously 8 bits. Time to live was 8 bits, and they felt that the world has not become any longer, and therefore 8 bits, which is 256 hop, is good enough. And the next header could be TCP, UDP, 6 is TCP, 17 is UDP. There are many other numbers which belong to IPv6 itself. And there are other protocols that could write on IPv6. But this basically indicates what is the thing, what is the next thing after this header. All right. So now the question is, how do you go from IPv4 to v6? Now this protocol IPv6 was designed by students from MIT and Stanford, and so it missed some of the key design things. Actually, I was working at Digital at that time, and our boss, who was really anti TCP/IP because we were trying to sell DECnet, he said that IPv6 will have this problem. And it does have that problem of transition. They didn't think about the transition. And the issue was that whenever you design new thing, you should make sure that the new thing can talk to the old thing and the old thing can talk to the new thing. Right? And these students didn't know. So basically, right now, the only solution to do IPv4 to v6 is that you implement both. And these people said, the designer said that, anybody can just implement both. What is the big deal? And that is not what is done. And that's why IPv6 is having so much difficulty. 1995 to 2019, 2020, let us say 20.25 years, and IPv6 is still not here. It's still not here in the sense that it is there in China and other countries where there are no IPv4 addresses. But in the United States, as long as we have IPv4 addresses, people are going to stick to it. And in fact, another big lease was given to IPv4 by the private addresses. Even in other countries, they are using IPv4 because private addresses have reduced the need for for global addresses. So anyway, the solution here was dual stack. Dual stack means that the routers will implement both IPv4 and IPv6. And so they are both IPv6 and v4 aware. Now that is one thing which is not happening, because even though all the hosts are IPv6 v4 aware, if you look inside your computer, inside your Windows, inside your Mac, they have both v4 and v6. Okay, even when you say IP config, it will tell you your IPv6 address. So IPv6 is there in the host. It is easy to change in the host, but nobody goes to the closets and changes the router ever. And so the routers don't have it. And if one router along the way does not have it, you cannot use it. And so that's where it is broken, is that IPv6 needs to change. The whole world needs to adapt to IPv6, and that will take few generations, if ever. So another solution is to tunnel, which is commonly used, is that if you are IPv6 and you have to go through IPv4 land, or through a router or through a set of router or through a country which does not use IPv6, you dig a tunnel through it. And what that means is that at the entry port, you put the whole IPv6 packet inside an IPv4 packet. This is called encapsulation. You encapsulate it, and then an IPv4 packet will go through that country or that set of routers. At the exit port, and here by port, I really mean the exit router, basically, not really the TCP port. At the exit point, the exit router will decapsulate this packet and send the original IPv6 on its way. Okay. And you can think about the similar thing being done for IPv4 going over IPv6. If I have IPv4 packet and that needs to go over IPv6, we will encapsulate it in an IPv6 packet. It will go over the IPv6 land, and at the other end, it will be decapsulated. So this is called tunneling. Tunneling because the IPv6 has no idea of what is happening inside in this. This looks like a wire to them. Okay. And this will be used, the tunneling is a common technique to use for any new feature in IP. If you put a new field in IP header, IPv4 or IPv6 header, that field will not be recognized by the older routers, and therefore you will need to tunnel it. Means you will have to develop a header which does not use that field, go through the other land and come out, and then put that field back again. Okay, so 2 questions. First of all, is it clear what does dual stack means? Dual stack means that the routers will have to understand both IPv4 and IPv6. And when they look at the first field, which says the version number is 6 or 4, then they will handle the rest of the packet accordingly. The second thing is tunneling. Tunneling is required, and basically whenever you need to go through an area where the IP version, it doesn't have to be version, just the IP flavor, as we say, is different, then we have to put it in encapsulation. So another name for encapsulation is tunneling. Is that clear? Somebody has to shake the head or something so that I know it is clear, otherwise I wouldn't know. All right, any questions? So when you have raised 2 hands means good. All right. So here thing that I'll tell you another example of tunneling would be, suppose I have I give this example. It's not in the book, but I will give it to you. Suppose I want to send something to, let's say a country. Let's say I want to send something to Japan, okay, and it goes through Korea, but the Koreans don't speak English. Actually, they do very good English, but I'm just going to assume that they don't speak English. I have my address which is written in English, but it has to go to Japan. So what we will do is, as soon as it reaches Korea, that my letter, which is actually an envelope, will be put into another envelope, a bigger envelope, and they will write the address in Korea saying that deliver this packet to the exit port of whatever is next to Japan in Korea. And the packet will go through Korea using that Korean address. And then at the other end, the Korean envelope will be taken out, and then English envelope will be sent. Actually, it turns out in this example that I have done, probably the Japanese won't speak English either, so then it has to be put into some Japanese envelope. But this is the kind of thing we do, is that whenever we go through a land where that language is not spoken, we put it into another envelope. Okay, and that is called encapsulation or tunneling. All right, so next. So that really brings us to the end of IPv4 v6. v4, key thing to remember is 32-bit addresses, and they are divided into 2 parts now, subnet part and the host part. Previously they were classes, but now we don't use it. And the private addresses are used. And now there are 3 private addresses, and you should remember them. Okay, so that goes on your cheat sheet. What are the 3 private addresses ranges that have been assigned? Remember 10.000, 172 point something, and then 192 point something, right? Then DHCP is used to automatically allocate addresses, and IPv6 uses 128-bit addresses, and that requires a dual stack, and so forth. Now, this basically, I just want to make sure that you read the fine print at the bottom, which is in red, which says read section 4.3 of the textbook, R17 through R29. Now, these are some very simple exercises, R17 through R29. I'm not going to give them as a homework, but you should try them, and those will be just considered like optional homework or whatever. Okay, so please read that section. Any question before we move on? Raise your hand. If you have a question, then raise your hand. That way I can see. Okay, go ahead. No, on Wednesday, this will none of this chapter will be covered. Sorry, when I said cheat sheet, this will be for the next exam cheat sheet. Okay. In the exam on Wednesday, we will cover only up to chapter 3. Everything up to chapter 3 will be covered, including the things that I asked you to read at home, such as, I think it was Skype and other things. There were something like, there were a few things that I had said that you have to read. So make sure that you read complete chapter 3. All right. Now, So this part, SDN, I don't think this is in version 6 of this book, or the edition 6th edition of this book. So if you have an old edition, you will not have this SDN stuff. I want to make sure that you somehow read it about it in the new version, a new edition of the book, or listen to my lecture carefully. All right. And SDN, actually, my lecture does not follow the book, because we have been through very detailed discussion of SDN, and when the SDN was being developed, we started giving lectures on SDN right here. And so some of our lectures are much better than the book, okay, at least in our view, okay, personal view. So first of all, there are 3 planes of networking that we will talk about, or 3 or 4 planes, and then we will talk about what is the data and control, and then we'll talk about the OpenFlow, which is related to SDN. SDN is software-defined networking. So the data plane. So basically what happens is there are 4 planes, because the data plane is anything that we have to do for the customer, for the user. So the user is sitting on the top, and whatever it sends, we have to, those bits, whatever we do for that, that is data plane. However, to make that happen, there are a lot of things that we have to do, even if there was no user. And so the control plane is all the activities that are necessary to perform the data plane activity, but does not involve any of the end user data packets. So one of the control plane activity would be making a routing table. So making a routing table is a control plane, because making the routing table does not require any user bits. It's basically we find the routes to all the places and hope that there are users will go there, and it's a control plane activity. However, making the packet from application layer to TCP to this and that and forwarding it, that is all data plane. Okay, so the data plane is forwarding, fragmentation and reassembly, and replication for multicasting. And so we didn't talk much about the multicasting, but the idea is that if you were to send a packet to many people, then you will just make copies of them along in the routers, and though that is all part of the data plane, because they all have user bits in them. Control plane is like making routing tables, setting packet handling policies, security policies. Okay, when you do something in the firewall. Base station beacons, announcing availability of services. So when you have a Wi-Fi base station, they keep announcing that, okay, Wustel encrypted 2.0 is available here, Wustel guest is available here. All those are control plane activities. Okay. Third plane is management plane. Now, management plane is also the activity which does not require any user bits. However, management plane is something that is optional. So, for example, actually we say in the offices, like in the office, if you didn't have your manager, the work will continue. However, what will not happen is if somebody becomes sick, then who will ask somebody else to take over? For that, we need a manager. So basically, management is required only when the things are not going the right way. Otherwise, if everybody does their job and everybody is healthy, everybody is good, then we don't need any managers whatsoever. So the managers are basically overhead, and they are actually charged as overhead in the company book sheet as well. But here in the routing, networking, anything that we do for this kind of things is called management, and that includes fault detection, configuration, accounting, performance, and security. So this is called FCAPS. FCAPS is fault, configuration, accounting, performance, and security. When you have a new device, you need to bring it up. That is management. And so all of this is optional. Okay. And you don't have to do it if everything is going well. And in fact, when you buy a router for home, mostly the management is missing, because nobody manages them at home. So you just come, plug it in, and it works. Whereas if you buy a router for your data center, it comes with a lot of management. When you put the router, you have to set it up, you have to make sure that it is monitored, you always check how many packets have been sent, if the packets are not being sent, why they are not coming. All of that is management. Okay, services plane. Now after this, then there is a fourth plane, which is generally not talked about much, but that basically is to improve the performance. Basically to improve performance. If you don't have that plane, performance will be bad, but things will go. So for example, load balancer. Generally what we do is instead of one server, we put 5 servers and we put a load balancer in the middle so that a lot of people can get serviced. Intrusion detection is the security thing, right? Proxy service. Proxy is again for performance. We put a proxy server like we said for HTTP so that people can get things faster. SSL. SSL is again security offloader. So there are many devices that will just do the security and make it faster. Firewalls. So these are also services plane, and these are also optional. They are not management because they improve the performance, but I mean, like, still, the control plane is essentials. So here's the thing, basically going back to this data plane and control plane. Data plane is required and the control plane is required. Without control plane, the network will not go anywhere. The packets will not go anywhere. Okay. So everybody understand these 4 planes? All right. So the data versus control logic. So was there a question? No raised hands. Okay. Data versus control logic. So what happens in the router is the data is coming at very fast rate, 10 gigabits or 100 gigabit. And therefore the data is done in the hardware, and it is a data logic is very fast. It's designed so that we can do gigabits per second. The control logic, like making the routing tables, doesn't have to be done at 10 gigabits. That is done at a slow speed, and that is done in a CPU. That is done in a CPU, central processing unit. And that could be a general purpose CPU, like Intel CPU. And so data plane runs very fast, and as much as it is possible is done in the hardware, whereas the control plane is done in a slow path. And so all control logic is handled by the CPU, right? So there's a data logic and the control logic. So the key idea that came, actually it came from Stanford. So, and this is one of the PhD theses where he came up with the idea that we should separate the 2 planes and centralize the control plane. And so here is what it looks like. So from each router, we divide the router, which is called switch, which is same thing. Switch is the layer 2 device. So Ethernet switch, for example, but it could be a router. We take the control and take it away from the switch and put it into a central place. So the only thing we have left is the data plane, and we call them forwarding elements. So these people, all the routers and the switches on the way, they don't do any making of the tables. Tables are not made there. They just use the table. The table is made in some central place and then sent to these places. So somebody can make the tables for every router and send it to those routers. Okay. And the protocol that is used to send those tables is called OpenFlow. So the control logic is moved to the controller. The switches only have forwarding elements. One expensive controller. So basically this would be, something that will have a lot of power. It has to make hundreds of routing tables. So it could be one expensive controller with a lot of cheap switches. Now these switches will not have any complications of the control. So they would be cheap. And the OpenFlow is the protocol that is used to send those tables. So how does OpenFlow work? So the OpenFlow works as follows. Basically, a table is sent, and the table consists of the header fields. It says that match the header. If it matches these fields, then counters, then you count these, increase these counters, increment these counters, and take these actions. So there are lots of fields, lots of header types or header variations. And for each variation, if it matches, then you do count this and then do this action. So what is a header field? Header field could be ingress port, what port it came on, ether source, what ether source address, what is the Ethernet destination address, what is the VLAN ID. And now we haven't talked about VLAN, so just think about that for a minute. Virtual LANs. This is all comes in layer 2. VLAN priority, and then IP source address. Now, by the way, this ingress port is not TCP port. Ingress port is the ingress interface, what wire it came on the router. Okay, and then there is a IP source, IP destination, IP protocol type, IP type of service, source TCP port, destination layer 4 port, I mean, not TCP, because UDP also uses the same port. So these are the port numbers. So all of these fields are matched with the header fields, and if they match, then you do the things which are specified by the counters and the actions. So here is a way to, here is a sample table. The table is, by the way, this table I don't think is in the book. Okay, so just listen carefully. If it is not clear, ask now, because this lecture we prepared in 2009 or 10, and it has been viewed by thousands of people on YouTube, and I have gotten lots of good comments and so on and so forth. So this is basically the best explanation of what it is done. But anyway, so it says port star, means it doesn't matter what port it came on. It doesn't matter what is the MAC address. But if the destination MAC address is 0A colon C8 colon anything followed by that, then this matches. VLAN ID doesn't matter, priority doesn't matter, ether type doesn't matter, source IP doesn't matter, destination IP doesn't matter, IP protocol type doesn't matter. And then the action is, and see, the destination L4 port doesn't matter. So as long as something comes with the destination address of A0AC8, beginning with 0AC8, what we do is we send it to port 1. Okay, now here is the problem. The port is used for both TCP port or L4 port or for the interface. So here we really mean interface. Unless otherwise indicated, we will generally use L4 port for TCP port, otherwise it is just the interface. So we send it to the interface number 1 and increment the counter 102. The second line says, it doesn't matter what are these fields, but if the destination IP is 192.168, they begin with that, then send it to the interface 2. Okay, and the counter number 202 goes up. The third line says, it doesn't matter what is all of these fields, except if the L4 port is 21, the source and destination both are 21, then you drop the packet and count 420, and so on and so forth. Okay, so the routers kind of keep matching with one of the with serially, and as soon as they match, they take the action. Okay, and so now this table will keep becoming big and big because as more and more entries are added, so there is an idle timeout. That means that if no packet is received for this time, suppose no packet matches, this counter doesn't go up at all. Some counters are 0 for 3 days. Then we remove that entry. Okay, hard timeout. And if some counter has been there for 5 days, we just remove it regardless. Whenever it has been used, we have to have the new table. Okay, so there is a hard timeout. If both are set, the entry is removed if either one expired. So basically, if the controller, when they send the table, it will put these timeouts. It will say, okay, this is good for next 1 hour, and hard timeout is 1 day. But so after that time, the entry goes away. Okay, and then you can ask the controller what is the new entry, or the controller will itself send a new entry, because if it is smart enough, it will know that the entry is not there anymore. So this is how the table works. The matching works as follows. Again, this matching is not in the book, but here it is how it works. It's set the input port. So basically when the packet comes, we set the input interface. So we say it came on wire number 1. And we take out the Ethernet source Ethernet destination, Ethernet type, and set all others to 0. Okay, in the Ethernet. Okay, is the ether type 0x8100. So this is in Ethernet, there is a field called ether type. If that is 8100, that means it has a VLAN. If it has a VLAN, then we look at the VLAN tag. If it is not a VLAN, then we see if the Ethernet type is 0806. If it is 0806, that means it is an IP packet, and therefore we look at the IP source, IP destination, IP protocol type, and so on and so forth. If it is not 0806, is it 0800? If it is, then it is also IP, and then we do this. Anyway, and then the matching is done. You see from here, if it is VLAN, then we just do something and then go back into the flow. If it is IP, then we come back here and we look up in the table, and if the table is, depending upon that, we take the action. On the other hand, if it is a fragment, it is not a fragment, then we see whether it is protocol type 6 or 7, which means that this is TCP or UDP. Then we look at the L4 ports. If it is protocol type 1, then it is ICMP, and so on and so forth. So there is a lot of logic. You don't have to remember this logic, but you can see that all this has to be done on the packet when it comes to match with one line, right? And then the counters. So there are counters for active entries, which entry has been used. So you increment the counter saying that this line has been used. Packet lookups, when they match, there are for each flow there are counters. For each port, means for each interface there is a counter. How many packets were received, how many packets were received with errors, how many packets were received without errors, and so on and so forth. For each queue there is a counter, because for each wire going out there are many queues, maybe 5 priorities, so there are 5 queues. For each queue there is a counter. So there are lots of counters, and each counter is numbered, and you have to increment that. The actions. The last part of the table here, the actions may be like this. It may be forward to the physical or virtual interface I. Whenever I say port here, I mean the interface I. So send it to the wire number 1. The wire may be physical or virtual. It may not be a real wire, because there are some virtual wires as well. So there are some interfaces which are not real. NQ, put into a queue, drop the packet, modify the field, mask allowing matching field and only selected fields. So masking, so you just mask these fields out and then do matching. If the header matches an entry, corresponding actions are performed and the counters are updated. If no header matches, the packet is queued. Now this is the important part. If no header matches, so we don't know which line to match, then the packet is put into a queue and the header is sent to the controller. The header is sent to the controller, which sends a new rule which says how to handle this kind of flow. And the channel between the controller and the switch is secure, so nobody can basically do it in the middle. So for example, this is the controller and this is this switch. This has to be very secure, because if somebody else puts some table here, they could just mess up the whole network. So this has to be secure. All right. So what we have done is there are lots of actions, and there are, all these are documented in like any other protocol documents. OpenFlow has many versions. For each version, there are actions, and so action actually continues. So let me finish these 3 more actions, and then we can talk about the actions. Modern switches already implement flow tables, typically using TCAMs. So what the idea is that all this matching that we said is done using TCAMs. TCAM can look up all this ether type and etc., and say what is matching. And controllers can change the forwarding rule if a client moves. So if, let's say, I am connected to this switch here, let's say this switch, and then I move to that switch, then the controller will say send all the packets for that particular MAC address to this place. So it can be changed as the people move. All right. And controller can send flow table entries beforehand, proactive, or send on demand. So I said in the previous slide that if something doesn't match, we have to send it to the controller, and then the controller sends you a response. That is called reactive. So the controller reacts to whatever situation comes up. But the controller could see all this beforehand and could imagine that, oh, somebody might come up with this kind of flow and send it beforehand, and that is called proactive. And both are used, both are allowed. Proactive, you can fill it before, and you can fill it later. So these are all the basically things about the OpenFlow, and this is called software-defined networking. Why it is called software-defined networking? Because this controller can be has a software with that you can change anything in the network. If you want people to not go one way or go to other way, you want some routers to be taking different paths, some packets to take different path. All of that can be done in one place. SDN, software-defined networking. Whole thing is done in one place, controller. Okay. All right. Now I have gone through many slides non-stop. Any questions about this before I go to the summary? Raise your hand before you say anything. Yeah. Okay, so I heard, are they one such controller? That part. The first part, are the controllers what? Say it loudly and clearly, maybe it will come through. Okay, are the controller located regionally or there is a global controller? Is that the question? Okay, no. So basically, the controllers would be basically under one management. And so they would not be global. You will have, everybody manages one network. For example, I manage my home's network, so I will have a controller in my home. In WashU, for example, CSE manages its own networks. It has its own basically staff. They will have their own controller, and if they are in 5 buildings, they might have 5 controllers. So the controllers are basically whatever part of the network you want to manage, you can have a controller for that part. There is no such thing as global controller, and nobody will want somebody else to use. So for example, while each department has their own controller, there might be a WashU controller which may talk to these controllers and tell them that, okay, from today Jain has resigned, so all his packets will be dropped or whatever. So the idea is there might be some other controllers which may decide the policies and communicate to others, but the controllers as shown in this picture are very local. Okay, all right, if there are no questions, then this is the data plane summary. Data plane consists of packets sent by the users. OpenFlow separates the data plane from the control plane and centralizes the control plane. The controller makes rules for forwarding and sends to switches. So basically, controller makes all the tables and the rules, and the switches match the rules and take the specified actions. Now you have to read the book. You have to read the book. If there are any questions, you can bring them to the next class. The description in the book is little bit different and out of date as well, because these things change by the year. So the book has tried to keep it up to date up to the year then it was written, and it takes 2 years to write a book, so it was written up to 2 years before that, and now things have changed significantly. So basically that's why you need to read that. But anyway, now this is the summary of the whole chapter 4. And I think this is also the time. So let me just finish this quickly. Chapter 4 summary is that the forwarding consists of matching the destination addresses, and the routing consists of making that table. So we said that many times. IP is a forwarding protocol. IPv4 uses 32-bit addresses. IPv6 uses 128-bit addresses. DHCP is used to assign the addresses. That is what we talked about today. Before that, we talked about the NAT. NAT is used to use single public address, and it basically uses the port numbers to keep track of who is talking to whom. And then the OpenFlow is used to separate the data plane from the control plane. Now, somebody had asked on Piazza questions about Lab 4A. They had not read these slides. Please read this slide. I was going to answer that. Please read the hints on Lab 4A. There are plenty of hints here. If you read that, it will tell you how to create 2 entries on your on your two interfaces on your computer. Okay, that is the end of the lecture today.